Hello there, and welcome to Math for Sleep. I'm so glad you found your way here tonight. Maybe you're already settled in, tucked under something soft and warm, or perhaps you're just beginning to wind down after a long day. Maybe your room is dark, or maybe there's a soft glow from somewhere nearby, just enough to see the shapes around you. However you've arrived, you're welcome here. Tonight, we're going to wander through something strange and beautiful, something that has puzzled mathematicians, philosophers, and curious minds for thousands of years. We're going to explore infinity, not to solve it, not to master it, just to move through it gently, the way you might walk through a quiet forest at dusk, noticing things without needing to hold on to them. We'll ask a question that sounds simple, but opens into something vast. Where do numbers go when they become infinite? You don't need to follow every word. You don't need to understand every concept. There's no test waiting at the end, no grade, no pressure. If your mind wanders, that's exactly right. If you drift off to sleep halfway through, that's perfect. The mathematics will still be there tomorrow, patient and constant, turning without you. Tonight is just for rest, for letting your thoughts slow down, for finding a gentle place to land. Before we begin our journey, if these quiet mathematical explorations help you find peace at night, consider giving this video a like or subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. And if you're still awake at the end, I hope you'll let me know in the comments where you're listening from tonight. A quiet bedroom, a cozy apartment, somewhere far away. It's nice to know we're all floating through this together, from different corners of the world, all looking for the same thing: rest. Now let's begin slowly, gently, one thought at a time. No rush, no hurry. We have all the time in the world. In fact, we have more than that. We have infinity. Imagine you're standing at the beginning of a very long road. You can see it stretching ahead of you, perfectly straight, heading toward the horizon. You take a step forward, then another, then another. You could keep walking like this forever. The road never ends. There's always more road ahead, always another step to take, always somewhere further to go. This is one way to think about infinity. Not as a place you arrive at, but as a direction that never stops. It's not the biggest number you can imagine. It's not a number at all. It's the idea that no matter how far you go, there's always further. No matter how much you count, there's always more. No matter how long you walk, the road continues. When you were very young, maybe you learned to count 1, 2, 3, 4. Maybe you counted your toys or steps or cookies. And maybe at some point you wondered, what's the biggest number? You might have said 1,000,000. Then someone told you about 1,000,000,000, then 1,000,000,000,000. Then you realized with a kind of dizzy feeling that you could always add one more. There's no end to it. The numbers just keep going. That feeling, that slight vertigo when you realize the numbers never stop, that's your first encounter with infinity. It's everywhere in mathematics, hiding in plain sight. It's in the counting numbers that go on forever. It's in the fractions between 0 and 1, packed so densely together that you could never list them all. It's in the decimal expansion of pi, which never repeats and never ends. Infinity isn't rare or exotic. It's woven into the fabric of numbers themselves. But here's where it gets interesting, where it starts to feel like a gentle mystery rather than just an endless road. Not all infinities are the same. Some infinities, strange as it sounds, are bigger than others. There are infinities you can count, in a sense, and infinities so vast that counting them is impossible, even if you had forever to try. This isn't just mathematical wordplay. This is real. It was discovered by a German mathematician named Georg Cantor in the late 1800s, and it changed everything. Before Cantor, infinity was something people talked about in hushed philosophical terms. It was the realm of God, of the eternal, of things beyond human understanding. Cantor brought it into mathematics. He showed that you could study infinity rigorously, carefully, the way you might study triangles or equations. And what he found was so surprising, so counterintuitive, that many mathematicians at the time refused to believe it. They said he was wrong. They said he was dangerous. Some said he was mad. But he wasn't. He was right. And the world of mathematics would never be the same again. Let's start with the simplest infinity, the one you probably encountered first, the counting numbers. 1, 2, 3, 4, 5. You know how this goes. It goes on forever. There's no last number, no place where the counting stops. This infinity has a name in mathematics. It's called Aleph Null. It's written with a Hebrew letter followed by a subscript 0. Aleph Null, the first infinity, the smallest infinite number. Now you might think, wait, how can an infinity be small? Isn't infinity, by definition, the biggest thing there is? And that's a good question. It shows you're paying attention. But infinity doesn't work the way finite numbers do. When we say Aleph Null is the smallest infinity, we don't mean it's small in the way 5 is smaller than 10. We mean it's the first kind of infinity you encounter when you start counting. It's the infinity of things you can list one after another, even if the list never ends. Think about the counting numbers again. 1, 2, 3, 4. Now think about the even numbers. 2, 4, 6, 8. These also go on forever. There are infinitely many even numbers, just as there are infinitely many counting numbers. But you might think, wait, there are fewer even numbers than counting numbers, right? Because the even numbers are only half of the counting numbers. We're skipping all the odd ones. This seems obvious and wrong. It turns out the even numbers and the counting numbers are the same size, not approximately the same size, exactly the same size. They have the same cardinality, which is the mathematical word for the size of a set. Both sets have Aleph Null members. Both are countably infinite. How can this be? How can you take half of something infinite and still have the same amount? The answer lies in a clever idea. You can pair them up. For every counting number, there's exactly one even number. 1 pairs with 2, 2 pairs with 4, 3 pairs with 6. You can march through the counting numbers, one by one, and for each one, you can point to a unique even number. This one-to-one correspondence shows that the two sets are the same size, even though one is a subset of the other. This is the first strange thing about infinity. You can remove half of an infinite set and not make it any smaller. You can take away infinitely many things and still have just as many things left. Infinity doesn't shrink. It doesn't get smaller when you subtract from it. It stays infinite, stubbornly, perfectly infinite. Now, let's think about the whole numbers. Not just the counting numbers, but all the integers, negative numbers, 0, positive numbers, -3, -2, -1, 0, 1, 2, 3. This set also goes on forever, but in two directions now. It stretches infinitely to the left and infinitely to the right. Surely this set must be bigger than the counting numbers, which only go in one direction. And yet, no. The integers are also countably infinite. They also have cardinality Aleph null. You can list them in a way that pairs each integer with a unique counting number. You might list them like this: 0, 1, -1, 2, -2, 3, -3, 4, -4. You're alternating between positive and negative, working your way outward from 0. Every integer appears exactly once in this list. Every counting number points to exactly one integer. The sizes match. This is deeply weird if you think about it. The integers include all the counting numbers, plus infinitely many negative numbers, plus 0. And yet they're the same size as just the counting numbers alone. Infinity absorbs everything. It doesn't get bigger when you add to it. It stays infinite, calmly, patiently infinite. Let's go further. What about fractions? Surely there are more fractions than whole numbers. Between 1 and 2 alone, there are infinitely many fractions. 1.5, 1 1/3, 1 1/4. You could keep going forever, finding fractions that get closer and closer to 1, or closer and closer to 2, never quite reaching either. The fractions are dense on the number line. They're packed together so tightly that between any two fractions, you can always find another fraction. They fill in all the gaps between the whole numbers. So fractions must be a bigger infinity, right? There must be more fractions than whole numbers. And again, no. The fractions, the rational numbers, as mathematicians call them, are also countably infinite. They're also Aleph null. You can list them. It takes a clever trick, but you can do it. You arrange them in a grid with all the fractions that have a denominator of 1 in the first row, all the fractions with a denominator of 2 in the second row, and so on. Then you zigzag through this grid, counting as you go. Every fraction appears in this grid somewhere. Every fraction gets counted eventually, even though the counting takes forever. This is astonishing. The fractions seem so much more numerous than the whole numbers. They seem to fill the number line completely, and yet they're the same size. Aleph null, countably infinite. You can put them in a list, one after another, even though the list never ends. It's worth pausing here, because this idea is so strange. The fractions are dense on the number line. This means that between any two fractions, no matter how close together they are, you can always find another fraction. Take 1/2 and 1/3. Between them lies 2/5 and 3/7 and 5/12 and infinitely many others. You can keep zooming in forever, finding more and more fractions packed into smaller and smaller spaces. And yet, despite this density, despite the fact that the fractions seem to fill every possible gap, they're countable. You can list them. The trick is to be clever about it. You arrange the fractions in a grid, ordered by their numerators and denominators. The fraction 1/2 goes in the first row. Second column. The fraction 2/3 goes in the second row. Third column. Every positive fraction appears somewhere in this infinite grid. Then you count the grid by moving along diagonals. You start at 1/1. Then you move to the second diagonal, 2/1. Then 1/2. Then the third diagonal, 3/1, 2/2, 1/3. But you skip 2/2 because it's the same as 1/1, which you've already counted. You only count each fraction once, in its reduced form. This diagonal path through the grid eventually reaches every fraction. It might take a while to get to 97/63, but eventually you'll reach it. This means the fractions are countable. They're Aleph null, the same size as the natural numbers, the same size as the integers, the same size as the even numbers. All of these infinite sets can be put into one-to-one correspondence with each other. They're all the same kind of infinity. But notice what you're doing here. You're using a very particular technique, a careful arrangement, to show that the fractions are countable. You can't just list them in order of size, because there is no next fraction after 0. You can't just march through them systematically in the obvious way. You have to be clever. You have to find a pattern, a path through the infinite grid that touches every fraction exactly once. This cleverness, this need for a special technique, is a hint that we're approaching the boundary between countable and uncountable. The fractions are just barely countable. You can list them, but only if you're smart about how you do it. And when we move beyond the fractions to all the real numbers, that cleverness won't be enough. No technique, no matter how clever, will let you list all the real numbers. They're fundamentally, provably uncountable. At this point, you might start to think, maybe all infinities are the same. Maybe every infinite set has the same cardinality. Maybe Aleph null is the only infinity there is. And this is where Cantor comes in. This is where everything changes. Georg Cantor was born in 1845 in St. Petersburg, Russia, though his family was German. His father was a successful merchant, working as a wholesaling agent in the St. Petersburg Stock Exchange, a man of considerable wealth and cultural sophistication. His mother, Maria Anna Böhm, came from a family of musicians, and music filled their home. Georg himself became an accomplished violinist, inheriting his mother's artistic sensibility. The household was one of culture and learning, where the arts and sciences were valued equally, where curiosity was encouraged and excellence expected. Georg's father was Protestant, his mother Roman Catholic. Georg was raised in his father's faith, but questions of religion and spirituality would haunt him throughout his life. He grew up in a household where faith mattered, where the eternal and the infinite were not just mathematical concepts, but spiritual realities. This background would deeply influence his later work, his conviction that mathematics could reveal divine truths, that infinity was not just an abstraction, but a glimpse into the mind of God. When Georg was 11, the family moved to Germany. His father's health was failing. Unable to cope with the harsh Russian winters, they settled in Frankfurt, and young Georg continued his education in German schools. He showed exceptional talent in mathematics, a gift that was recognized early by his teachers. His father wanted him to become an engineer, a practical profession that would ensure financial security. But Georg knew, even as a teenager, that mathematics was his calling. He wanted to study pure mathematics, to understand numbers and patterns and abstract structures, not to build bridges or design machines. Eventually, his father relented. Georg enrolled at the University of Zurich, then transferred to the University of Berlin, where he studied under some of the greatest mathematicians of the 19th century. Carl Weierstrass taught him analysis, introducing him to the rigorous epsilon-delta methods that would become standard in calculus. Ernst Kummer taught him number theory, the study of the properties of the integers, and Leopold Kronecker, who would later become his bitter enemy, was also among his teachers. In 1867, at the age of 22, Cantor received his doctorate. His dissertation was on number theory, a topic suggested by Kummer. It was solid work, competent, but not revolutionary. Nothing in it hinted at what was to come, the revolution in mathematics that Cantor would unleash a few years later. After receiving his degree, Cantor took a position at the University of Halle, a small provincial university far from the intellectual centers of Berlin or Göttingen. He would remain at Halle for the rest of his career, never receiving the prestigious appointment he hoped for at a major university. This failure to advance to a more prominent position was partly due to Kronecker's opposition, partly due to the controversial nature of his work, partly due to his own mental health struggles. But despite these obstacles, Cantor did his most important work at Halle, creating set theory in relative isolation, driven by an inner vision of mathematical truth. In 1874, when he was just 29 years old, Cantor published a paper that would change mathematics forever. In it, he proved something that seemed impossible. He proved that some infinities are bigger than others. He proved that the real numbers, all the numbers on the number line, including the irrational numbers like pi and the square root of 2, cannot be put into a one-to-one correspondence with the counting numbers. The real numbers are uncountably infinite. They're a bigger infinity than Aleph Null. They're so numerous that you could never list them, not even if you had forever to try. This was shocking. This was heretical. Many mathematicians refused to believe it. His former teacher, Leopold Kronecker, attacked him viciously, calling him a charlatan, a corrupter of youth, a destroyer of mathematics. Kronecker was a powerful figure in German mathematics, and his opposition had real consequences. He used his influence to block Cantor's papers from publication, to prevent him from getting academic positions, to isolate him from the mathematical community. Kronecker's objection was philosophical. He was a finitist, someone who believed that only finite mathematics was truly legitimate. To Kronecker, actual infinity didn't exist. It was a linguistic confusion, a category error, a philosophical mistake. You could talk about potential infinity, the sense in which the counting numbers go on forever, but you couldn't treat infinity as a completed, actual thing. And certainly, you couldn't have multiple infinities of different sizes. That was nonsense, dangerous nonsense, the kind of thinking that would undermine the foundations of mathematics. But Kronecker wasn't alone in his opposition. The French mathematician Henri Poincaré, one of the greatest mathematicians of his era, called Cantor's set theory a beautiful pathology, a disease from which mathematics would one day recover. He saw it as interesting, perhaps, but ultimately misguided, a wrong turn that mathematics had taken and would need to retrace. Others were more sympathetic, but still skeptical. They acknowledged that Cantor's proofs were rigorous, that he had proven what he claimed to prove, but they questioned whether these proofs revealed anything true about the nature of reality. Maybe set theory was just a game, a system of formal manipulations that didn't correspond to anything real. Maybe infinity was inherently problematic, and trying to study it mathematically was doomed to paradox and confusion. These attacks took a terrible toll on Cantor. He was a sensitive man, deeply invested in his work, convinced that he was revealing eternal truths. The opposition he faced wasn't just intellectual disagreement. It was personal, vicious, aimed at destroying his reputation and his career. He began to suffer from depression, experiencing his first major breakdown in 1884 when he was 39 years old. From that point on, his mental health was fragile. He experienced recurring episodes of depression, sometimes severe enough that he needed to be hospitalized. During these dark periods, he couldn't work, couldn't think clearly, couldn't function. He would recover for a while, return to his research, make progress on his theories. Then another episode would strike, plunging him back into darkness. The relationship between Cantor's mental illness and his mathematical work is complex and contested. Some biographers have suggested that his obsession with infinity drove him mad, that wrestling with the endless broke his mind. Others have argued that his mental illness was biological, unrelated to his mathematics, that he would have suffered from depression regardless of what he studied. Modern historians tend toward the latter view, noting that depression often has genetic and biochemical causes, and that Cantor's illness followed patterns consistent with bipolar disorder. But regardless of the cause, the illness was real, and it was devastating. Cantor spent extended periods in sanatoriums, trying to recover, fighting against the despair that threatened to overwhelm him. During these times, he couldn't do mathematics. His mind, usually so sharp and creative, became clouded and uncertain. He wrote letters filled with paranoia and strange ideas. He developed an obsession with proving that Francis Bacon had written Shakespeare's plays, producing volumes of questionable scholarship on the subject. He wrote religious treatises, trying to reconcile his mathematical discoveries with Christian theology, arguing that his theories about infinity revealed truths about the nature of God. Through all of this, he never gave up on his mathematics. Even during his worst periods, he held on to his conviction that set theory was true, that his vision of multiple infinities was correct, that he had seen something real and important. And gradually, slowly, the mathematical community began to come around. Cantor suffered greatly under these attacks. He struggled with depression throughout his life, spending time in hospitals, fighting against the darkness that sometimes overtook him. Some have said his mental illness was caused by his obsession with infinity, that staring into the endless broke something in his mind. Others have pointed to genetic factors, to the strain of his academic battles, to the loneliness of being ahead of his time. We don't know. What we do know is that he kept working, kept pushing forward, kept exploring the infinite even when it cost him dearly. He believed his work was divinely inspired. He saw mathematics as a way to understand the mind of God. He thought infinity was sacred, that by studying it, he was glimpsing something eternal and true. And he was right, in a way. His work did reveal something profound about the nature of reality, about the structure of numbers, about the way the universe organizes itself. He opened a door that could never be closed again. Today, Cantor is recognized as one of the greatest mathematicians who ever lived. His set theory is foundational to modern mathematics. His ideas about infinity are taught to students around the world. But in his own time, he was often alone. fighting battles that seemed impossible to win, believing in truths that others couldn't see. He died in 1918 in a hospital, still working, still thinking about infinity. And the world kept turning, and his ideas kept growing, and mathematics was forever changed. Let's talk about Cantor's diagonal argument. This is the proof, the elegant, clever, devastating proof that showed some infinities are bigger than others. It's beautiful in its simplicity, it's devastating in its implications, and you don't need to be a mathematician to understand it. Just follow along, gently, and see where it leads. Suppose, just for the sake of argument, that you could list all the real numbers between 0 and 1, every decimal number, every fraction, every irrational number, all of them in one big list. You might start with 0.1, then 0.2, then 0.3. You're writing them down, one after another, each one with its own unique position in the list. First number, second number, third number, and so on. Each of these numbers has a decimal expansion. 0.1 is 0.1, 0, 0, 0, continuing forever with zeros. 0.1, 4159 is the decimal expansion of pi minus 3. Some numbers have decimal expansions that terminate, ending in zeros forever. Some have expansions that repeat, like 1/3, which is 0.3333 forever. Some have expansions that never repeat, never settle into a pattern, going on infinitely without rhyme or reason. Now here's Cantor's trick. He says, suppose you've made your list. Suppose you claim it's complete, that every real number between 0 and 1 is somewhere on this list. I'm going to construct a new number, a number that's definitely between 0 and 1, and I'm going to show you that it's not on your list. This will prove your list isn't complete. This will prove you can't list all the real numbers, no matter how hard you try. Here's how he does it. Look at the first number on your list. Look at its first decimal digit. Whatever that digit is, I'm going to choose a different digit. If it's a 1, I'll choose a 2. If it's a 5, I'll choose a 6. I'm just picking something different. That's the first digit of my new number. Now look at the second number on your list. Look at its second decimal digit. Again, I'm going to choose a different digit. Whatever it is, I'll change it. That's the second digit of my new number. Now the third number, its third digit. I'll change it. That's the third digit of my new number. And so on, forever. For the nth number on your list, I look at the nth digit and I change it. This gives me the nth digit of my new number. What I've constructed is a number that differs from every number on your list. It differs from the first number in the first digit. It differs from the second number in the second digit. It differs from the third number in the third digit. It differs from every single number on your list in at least one place. This means my new number is not on your list. You claim to have listed all the real numbers between 0 and 1, but here's a number you missed. Your list is incomplete. This argument works for any list you might make. No matter how you try to list the real numbers, I can use this diagonal trick to construct a number you've left out. This means the real numbers can't be listed. They can't be put into a one-to-one correspondence with the counting numbers. They're uncountably infinite. They're a bigger infinity than Aleph Null. This is the proof. This is the moment when mathematics split into countable and uncountable, when infinity revealed itself to have layers, depths, sizes that differ from each other. This is when the endless turned out to be more complicated than anyone had imagined. When Cantor first presented this argument in 1891, many mathematicians were shocked. Some refused to believe it. It seemed like a trick, like a clever sleight of hand that couldn't possibly reveal something true about the nature of numbers. How could the real numbers be a bigger infinity than the natural numbers? They're both infinite. Infinity is infinity, isn't it? But the proof is airtight. There's no way around it. If you claim to have a complete list of all real numbers between 0 and 1, Cantor's diagonal argument will produce a number not on your list every single time. This means such a list is impossible. The real numbers resist being counted, resist being put into a sequence, resist being matched one-to-one with the natural numbers. This was revolutionary. This changed the entire landscape of mathematics. Before Cantor, mathematicians avoided talking about infinity in precise terms. It was considered dangerous, imprecise, possibly meaningless. After Cantor, infinity became a legitimate object of mathematical study. You could prove theorems about it. You could make distinctions within it. You could understand its structure, even if you couldn't fully comprehend its vastness. And the diagonal argument itself is so simple, so elegant. It doesn't require advanced mathematics. You don't need to know calculus or topology or abstract algebra. You just need to understand what a decimal expansion is, what it means to make a list, and what it means for two things to be different. The proof is accessible to anyone willing to think carefully about it, and yet its implications are profound, revolutionary, world-changing. This is one of the beautiful things about mathematics. Sometimes the deepest truths have the simplest proofs. Sometimes the most profound insights come from thinking carefully about basic concepts. Cantor didn't invent new machinery to prove his theorem. He just looked at something familiar, the real numbers, from a new angle, with fresh eyes. And he saw something no one had seen before. Let's sit with this for a moment. Let's think about what it means. The real numbers, all the points on the number line, are uncountably infinite. There are so many of them that you could never list them all, even if you had infinite time. They're more numerous than the counting numbers, even though the counting numbers go on forever. This means that between 0 and 1, there are more numbers than there are counting numbers in all of existence. Between 0 and 1, a distance so small you can mark it with your fingers, there are more numbers than you could ever count. They're packed in there, impossibly dense, filling every gap, leaving no space empty. And yet, if you were to pick a random real number between 0 and 1, almost certainly it would be irrational. A number whose decimal expansion never repeats, never settles into a pattern. The irrational numbers are so much more numerous than the rational numbers that the rationals almost disappear in comparison. This is a strange thought to hold in your mind. The rational numbers, the fractions, seem so abundant. They're dense on the number line. Between any two of them, you can find another. They seem to fill everything. And yet, in the grand scheme of things, they're sparse, they're countable, they're just aleph null. The irrational numbers, the ones that can't be written as fractions, they're the vast majority. They're uncountable, they're everywhere, filling the number lines so completely that the rationals are like isolated points scattered across an infinite ocean. You're lying there right now, in your bed, in your room, and maybe you're thinking about the space between your hand and the wall. That space can be measured. It might be a few feet, or a few meters, or a few centimeters. But within that space, there are uncountably many points. More points than you could ever count. More positions than there are counting numbers. The continuous is richer, deeper, more infinite than the discrete. The smooth is vaster than the granular. Physicists sometimes ask whether space and time are continuous or discrete. Are they smooth, filled with uncountably many points? Or are they grainy, made up of tiny, indivisible chunks? We don't know. But mathematically, the continuous is bigger. The continuum, as it's called, has a higher cardinality than the countable. It's a deeper infinity, a more profound endlessness. There's a thought experiment that helps illustrate the difference between countable and uncountable infinity. It's called Hilbert's Hotel, and it was invented by the German mathematician David Hilbert in the 1920s. Imagine a hotel with infinitely many rooms. Room 1, room 2, room 3, and so on, forever. Every room is numbered with a counting number. There's no last room, no end to the hallway. It just keeps going. Now suppose the hotel is completely full. Every room has a guest. Every single one of the infinitely many rooms is occupied. You might think, well, that's it. The hotel is full. There's no room for anyone else. If a new guest arrives, they're out of luck. There's nowhere to put them. But this is an infinite hotel, and infinite hotels have strange properties. The manager says, no problem, we can make room. She asks every guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. Every guest shifts over by one. Since there are infinitely many rooms, every guest has a room to move into. There's no last guest who runs out of space. Everyone just shifts over, and room 1 becomes empty. The new guest can take room 1. Problem solved. This seems impossible, but it's perfectly consistent mathematically. You've taken a completely full hotel and made room for another guest without anyone leaving. This works because the hotel is countably infinite. The rooms can be put into a one-to-one correspondence with the counting numbers. You can shift the correspondence, moving everyone over and still have room left. But it gets stranger. Suppose not just one new guest arrives, but infinitely many. An infinite bus pulls up with infinitely many passengers, all wanting rooms. The hotel is still full. Every room still has a guest. How do you make room for infinitely many new arrivals? The manager thinks for a moment, then smiles. She asks every current guest to move to the room with twice their current room number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. Every guest moves to an even-numbered room. This leaves all the odd-numbered rooms empty. 1, 3, 5, 7, 9. There are infinitely many odd-numbered rooms, and now they're all vacant. The infinitely many new guests can take the odd-numbered rooms. Everyone has a room. The hotel accommodates them all. This is the power of countable infinity. You can rearrange it, shift it, double it, and it stays the same size. Aleph null plus Aleph null equals Aleph null. Infinity plus infinity equals infinity, as long as you're talking about countable infinity. But we can push this even further. Suppose infinitely many buses arrive, each with infinitely many passengers. How does the hotel accommodate them all? This seems impossible. you have infinitely many current guests, plus infinitely many buses, each containing infinitely many new guests. That's infinity times infinity. Surely this exceeds the capacity of the hotel, even an infinite hotel. But again, there's a solution. It requires a more sophisticated technique, but it works. The manager assigns the current guests to rooms numbered with powers of 2. The guest in room 1 moves to room 2 to the power of 1, which is 2. The guest in room 2 moves to room 2 to the power of 2, which is 4. The guest in room 3 moves to room 2 to the power of 3, which is 8. Every current guest moves to a room numbered with a power of 2. Now, for the buses. The passengers on the first bus get assigned to rooms numbered with powers of 3. The passenger in seat 1 gets room 3. The passenger in seat 2 gets room 9. The passenger in seat 3 gets room 27. The passengers on the second bus get assigned to rooms numbered with powers of 5, the next prime number. The passengers on the third bus get powers of 7, and so on, using successive prime numbers for successive buses. This works because every positive integer can be factored uniquely into prime powers. A room numbered 24 equals 2 to the third power times 3 to the first power. That means it's occupied by… Actually, wait. This gets complicated because 24 has multiple prime factors. Let me think about this differently. Actually, a simpler way to handle infinitely many buses with infinitely many passengers is to use a pairing function. Imagine each passenger has 2 coordinates, which bus they're on and which seat they're in. The passenger on bus 1, seat 1, goes to room 1. The passenger on bus 2, seat 1, goes to room 2. The passenger on bus 1, seat 2, goes to room 3. You can create a systematic path through all possible bus seat combinations, ensuring each combination gets a unique room number. The point is, even though you're adding infinitely many infinities to the original infinity, you can still fit everyone in. The hotel never runs out of rooms because the number of rooms is infinite. You can keep adding guests, even infinite numbers of guests, and the mathematics works out. There's always a clever rearrangement that makes space for everyone. This is deeply counterintuitive. In the finite world, if you have a hotel with 100 rooms and it's full, adding even one more guest is impossible. But in the infinite world, you can add infinitely many guests, or infinitely many infinite groups of guests, and still have room. The infinite is fundamentally different from the finite. It doesn't obey our usual intuitions about size and capacity and fullness. Hilbert invented this paradox to help people understand countable infinity, to make concrete and visual something that otherwise feels abstract and slippery. And it works. The hotel is easier to think about than abstract sets and cardinalities. You can imagine the guests moving, picture the rooms filling up, visualize the solutions to each new problem. It makes the infinite feel manageable, even playful. But there's a limit to what Hilbert's hotel can do. It works because the rooms are countably infinite, numbered with natural numbers. Each room has a specific position in a sequence. This structure allows you to manipulate the guest assignments, to create bijections between infinite sets, to show that they're all the same size. But what if the hotel had uncountably many rooms? What if the rooms were numbered with all the real numbers, not just the counting numbers? Then the hotel would be a different beast entirely. You couldn't shift the guess the same way. The structure of the uncountable is different. It's less flexible, more dense, harder to manipulate. The tricks that work for countable infinity don't work for uncountable infinity. The two are fundamentally different in nature, not just in size. So we have Aleph Null, the cardinality of the countable infinite, and we have the cardinality of the continuum, the cardinality of the real numbers, which is bigger. Mathematicians sometimes write this as C for continuum, or as 2 raised to the power of Aleph Null. It's the cardinality of the power set of the natural numbers, the set of all possible subsets of the counting numbers. It's the next level of infinity, the next step up. But is it the next step? Is there an infinity between Aleph Null and the continuum? Or is the continuum the very next infinity, the one that comes immediately after Aleph Null? This is one of the most famous questions in mathematics. It's called the continuum hypothesis. Cantor believed the answer was yes, that the continuum is the next infinity, that there's nothing in between. He called this next infinity Aleph 1. He believed the cardinality of the continuum was Aleph 1. He spent years trying to prove it. He never succeeded. In 1900, the mathematician David Hilbert gave a famous lecture in Paris, listing 23 unsolved problems that he believed would shape the future of mathematics. The first problem on his list was the continuum hypothesis. Is the cardinality of the real numbers equal to Aleph 1? Or is there an infinity in between? For decades, mathematicians tried to answer this question. They tried to prove the continuum hypothesis. They tried to disprove it. Nothing worked. The question seemed to resist every approach, every technique, every clever idea. It was like trying to grab smoke. The answer slipped away every time. Then, in the 1930s, the Austrian mathematician Kurt Gödel made a breakthrough. He showed that if you assume the standard axioms of set theory, the Zermelo-Fraenkel axioms, plus the axiom of choice, then you can't disprove the continuum hypothesis. It's consistent with the axioms. If the axioms are true, the continuum hypothesis could be true. But that's not the same as proving it's true. That's just showing. It doesn't contradict the axioms. Maybe the continuum hypothesis is true. Maybe it's false. Gödel's result didn't settle the question. It only showed one half of the picture. Then, in 1963, the American mathematician Paul Cohen completed the picture. He showed that you also can't prove the continuum hypothesis from the standard axioms. It's independent. If the axioms are consistent, then both the continuum hypothesis and its negation are consistent with the axioms. You can have a mathematical universe where the continuum hypothesis is true, and you can have a different mathematical universe where it's false. Both are perfectly consistent. This was shocking. This meant the continuum hypothesis can't be settled within the standard framework of mathematics. It's undecidable, not in the sense that we don't know the answer, but in the deeper sense that the answer depends on which axioms you accept, which mathematical universe you're working in. There's no single truth about whether there's an infinity between Aleph Null and the continuum. The question itself transcends the framework. Some mathematicians were satisfied with this answer. They said, okay, the continuum hypothesis is independent. That's the end of it. We can work in whichever universe we prefer. Others, including Gödel himself, believed this just showed our axioms were incomplete. They thought there must be some deeper truth, some more fundamental axioms that would settle the question once and for all. The debate continues to this day. But maybe the question itself is the answer. Maybe the point isn't to know whether the continuum hypothesis is true or false, but to understand that mathematics can contain multiple consistent universes, each with its own truths. Maybe infinity is so vast, so profound, that it exceeds our ability to pin it down completely. Maybe there's a kind of freedom in that, a kind of openness. Think about what this means. Numbers, which seem so solid, so definite, lead us into a realm where truth itself becomes multiple, where different consistent answers exist for the same question. The infinite is not just big, it's slippery, it's elusive. It exceeds our frameworks, our systems, our attempts to contain it. Cantor believed he was glimpsing the mind of God when he studied infinity. Maybe he was right. Maybe the infinite is divine, not because it's large, but because it's inexhaustible. No matter how much you understand, there's always more. No matter how far you go, there's always further. The questions never end. The mysteries never resolve completely. There's always another layer, another depth, another infinity beyond the infinity you just discovered. This is where numbers go when they become infinite. They don't go anywhere. They don't stop. They multiply, they branch, they open into realms that contain other realms. Aleph Null leads to the continuum, which leads to Aleph 2, the cardinality of the power set of the real numbers, which leads to Aleph 3, and so on, forever. Each infinity gives birth to a larger one. Each level contains the levels below it and points toward the levels above it. The Tower of Infinities rises without end. And yet, for all this vastness, we can think about it. We can understand it, at least partially. We can make distinctions, draw maps, prove theorems. The infinite isn't completely beyond us. It's just beyond any final, complete understanding. We can know it without exhausting it. We can explore it without reaching its end. You're still lying there, maybe still listening, maybe drifting somewhere between waking and sleeping. Your room is quiet. Your body is heavy, sinking into the bed. Outside, maybe there's a sound, a car passing, wind in the trees. Or maybe it's perfectly silent, just you and the darkness and the slow rhythm of your breath. The numbers are still there, whether you think about them or not. 1, 2, 3, 4, counting upward forever. 0.1, 0.11, 0.111, filling the space between 0 and 1 with uncountably many points. Aleph Null, Aleph 1, Aleph 2, reaching upward into infinities so large they make Aleph Null look small by comparison. But you don't need to hold all of this in your mind. You don't need to understand every detail, follow every argument, grasp every implication. Mathematics doesn't ask that of you. It just invites you to wander, to notice, to wonder. It offers you landscapes to explore, not destinations to reach. You can walk as far as you like, and then stop and rest, and let the mathematics continue without you. Because it will continue. The numbers will keep counting. The infinities will keep rising. The questions will keep unfolding. Whether you're listening or not, whether you're awake or asleep, the mathematical universe goes on, patient and eternal, turning in its own perfect way. Cantor saw this. He understood that mathematics isn't something we invent. It's something we discover. The numbers were already there, waiting. The infinities were already real. existing in some platonic realm beyond time and space. We just had to learn how to see them, how to think about them, how to bring them into the light. And in doing so, we learned something about ourselves. We learned that our minds can reach beyond the finite, beyond the everyday, beyond the obvious. We can think about the endless. We can make distinctions within the infinite. We can find structure in the vast, order in the limitless, beauty in the incomprehensible. There's a kind of comfort in this, not because the infinite is familiar, but because it shows that reality is deeper than it seems. The world you live in, the one with bills and emails and traffic and weather, is just the surface. Underneath, supporting everything, is this mathematical foundation, this structure of numbers and infinities and logical relationships that holds it all together. You're made of atoms, and atoms follow mathematical laws. The space you occupy is continuous, filled with uncountably many points. The time you live through is measured by numbers that flow smoothly, second by second, moment by moment. You're embedded in this mathematical universe, whether you know it or not. You're part of the pattern, and the pattern is beautiful. It's intricate and elegant and surprising. It contains paradoxes that resolve into deeper understanding. It contains mysteries that open into further mysteries. It's a landscape you could explore forever and never see everything, never exhaust its richness. Mathematicians sometimes talk about the unreasonable effectiveness of mathematics. They mean that mathematics, which seems like a purely human invention, a game we play with symbols and logic, turns out to describe the physical universe with astonishing accuracy. The same mathematics that Cantor used to study infinity turns out to be essential for understanding quantum mechanics, cosmology, information theory. The abstract becomes concrete, the theoretical becomes practical, the infinite becomes useful. But maybe it's not unreasonable at all. Maybe mathematics is effective because the universe is mathematical at its core. Maybe numbers aren't just a tool we use to describe reality. Maybe they're part of the fabric of reality itself. Maybe when you count, when you measure, when you calculate, you're not imposing order on chaos. You're discovering the order that was already there. Think about pi. This number, the ratio of a circle's circumference to its diameter, has been known for thousands of years. Ancient mathematicians knew it was a little more than 3. They calculated approximations, better and better ones, getting closer and closer to the true value. We now know pi to trillions of decimal places: 3.141592653589979. The digits go on forever, never repeating, never settling into a pattern. Pi is everywhere in mathematics. It shows up in geometry, obviously, but also in calculus, in probability, in number theory. It appears in places that have nothing to do with circles. It's in the formula for the area under a bell curve. It's in infinite series that seem unrelated to anything circular. It's in solutions to differential equations, in Fourier transforms, in quantum mechanics. Pi is woven into the structure of mathematics itself, showing up wherever you least expect it. And pi is just one number. There are infinitely many others like it, each with its own properties, its own personality, its own strange places where it appears. Euler's number, E, the base of natural logarithms, the golden ratio, phi, which shows up in art and architecture and the spirals of shells. The square root of 2, which the ancient Greeks discovered, was irrational, proving that not all lengths can be measured by fractions. Each of these numbers is a door into a different part of the mathematical landscape. Each one leads somewhere, opens into something, and all of them together, all the real numbers, all the points on the number line, they form the continuum. They form an uncountable infinity, a set so vast that you could never list its members, never count them one by one, never exhaust them. This is where numbers go when they become infinite. They don't disappear. They don't become meaningless or abstract. They become more. They become richer, deeper, stranger. They become part of a structure that exceeds our finite understanding, but not our finite minds. We can think about them. We can study them. We can discover their properties, prove theorems about them, map the landscape they create. Maybe you're wondering, does any of this matter? Does it make a difference to your life, to your day-to-day existence, that some infinities are bigger than others, that the real numbers are uncountable, that the continuum hypothesis is undecidable? In a practical sense, maybe not directly. You won't use Cantor's diagonal argument to pay your bills or plan your week. You won't need to know about Aleph Null to decide what to have for breakfast. This is pure mathematics, abstract and theoretical, far removed from the everyday world. No one has ever been asked in a job interview to explain the difference between countable and uncountable infinity. No mechanic needs to understand Hilbert's Hotel to fix your car. No chef needs to know about transfinite cardinals to prepare a meal. But in another sense, maybe it matters immensely. Maybe it matters because the world you live in is fundamentally mathematical. The phone or computer you might be listening to this on right now operates on principles that depend on mathematics far more abstract than anything we've discussed tonight. The digital information that encodes this audio file, the zeros and ones that represent sound waves, the algorithms that compress and decompress that information. All of this rests on mathematical foundations that were built by people thinking about infinity and sets and abstract structures. The internet itself, this vast network connecting billions of devices, is possible because mathematicians in the 20th century developed information theory, a field that owes much to set theory and the study of infinite sets. When you send a message, when you stream a video, when you search for something online, you're using technology that couldn't exist without the abstract mathematics of infinity. Or consider physics. Our best theories about the nature of reality, quantum mechanics, and general relativity are fundamentally mathematical. They describe the universe in terms of continuous functions, infinite dimensional spaces, limits, and infinitesimals. The real numbers, with their uncountable infinity of points, are woven into the fabric of these theories. Space and time, as we understand them through physics, are modeled as continuous, as containing infinitely many points in any finite region. Are space and time actually continuous? Or is this just a useful mathematical approximation? We don't know. At the smallest scales, at the Planck length and the Planck time, quantum effects might make space and time discrete, granular, made of indivisible chunks. Or they might not. The question remains open. But the fact that we can even ask this question, the fact that we can distinguish between continuous and discrete, between countable and uncountable, is thanks to the work of mathematicians like Cantor, who made these distinctions precise. Beyond the practical applications, there's something deeper. Understanding infinity changes how you think about reality. It shows you that the universe is stranger than common sense suggests, that intuitions developed for dealing with finite things can mislead you when applied to the infinite. It teaches you humility, a recognition that your immediate perceptions don't always match the underlying truth. This is valuable, not just for mathematicians or physicists, but for anyone. Living in a complex world requires recognizing that things are often not what they seem, that surface appearances can be deceiving, that careful thought can reveal structures and patterns invisible to casual observation. Infinity is an excellent teacher of this lesson because it's so thoroughly counterintuitive. Every result we've discussed tonight contradicts naive intuition in some way. In a practical sense, maybe not. You won't use Cantor's diagonal argument to pay your bills or plan your week. You won't need to know about Aleph Null to decide what to have for breakfast. This is pure mathematics, abstract and theoretical, far removed from the everyday world. But in another sense, maybe it matters immensely. Maybe it matters because it shows you that reality is stranger and deeper than it appears. Maybe it matters because it reminds you that there are questions worth asking even if they can't be fully answered. Maybe it matters because it demonstrates that your mind can grasp something infinite, something that exceeds all finite boundaries. And in doing so, your mind itself becomes something more than finite. When you think about infinity, even for a moment, even in a vague, half-sleeping way, you're exercising a capacity that sets you apart from most of the natural world. You're thinking about the endless. You're imagining the unimaginable. You're reaching beyond the immediate, beyond the tangible, beyond the concrete. You're doing philosophy, theology, mathematics, all at once. And there's a kind of peace in that, a kind of quiet satisfaction. You don't have to understand everything. You don't have to solve the continuum hypothesis or prove theorems about transfinite cardinals. You just have to know that these things exist, that these questions are real, that this landscape is there, waiting for anyone who wants to explore it. Cantor knew this. Even when he was struggling, even when he was attacked by his peers, even when he was hospitalized and afraid and alone, he knew that he had seen something true. He had looked into the infinite and seen structure there, order, beauty. He had shown that infinity wasn't chaos, it was mathematics. It was knowable, at least partially. It was a gift. The mathematician David Hilbert, who was one of Cantor's supporters, once said, "No one shall expel us from the paradise that Cantor has created." He was talking about set theory, about the mathematical study of infinity. He was saying that this new understanding, this new vision of what mathematics could be, was too beautiful to abandon. It was a paradise, and we should live there, explore it, make it our home. And it is beautiful, not in the way a sunset is beautiful, or a piece of music, or a face, but beautiful in its own way, elegant, surprising, true, the kind of beauty that comes from seeing patterns, connections, relationships that no one saw before, the kind of beauty that comes from understanding. You don't have to be a mathematician to appreciate this beauty. You just have to be curious. You just have to wonder. You just have to ask the question, what happens when numbers become infinite? and then listen to the answer. Not to memorize it, not to test yourself on it, just to hear it, just to know that the answer exists. And the answer is this: when numbers become infinite, they don't stop being numbers. They don't dissolve into meaninglessness. They organize themselves into hierarchies, structures, levels. They create a rich, complex, endlessly fascinating landscape. They show us that infinity isn't one thing, it's many things. It's Aleph Null and the continuum and all the larger infinities beyond. It's countable and uncountable. It's the road that never ends and the dense collection of points that fills every gap. When numbers become infinite, they go everywhere and nowhere. They stay exactly where they are, on the number line, in the mathematical universe, in the structure of logic and reason. But they also exceed any boundary, any limit, any attempt to contain them. They're simultaneously graspable and ungraspable, knowable and unknowable, finite in our understanding and infinite in their nature. This is the paradox at the heart of mathematics. We use finite minds to study the infinite. We use limited tools to explore the limitless. And somehow, impossibly, it works. We make progress. We prove theorems. We discover truths. We build a body of knowledge that grows year by year, century by century, never complete, but always advancing. Your breath is slow now. In, out, in, out. Your body heavy, sinking deeper into the bed. Maybe your eyes are closed. Maybe your thoughts are drifting, detaching, floating somewhere between here and sleep. That's good. That's exactly right. Let them drift. Let them float. The mathematics can take care of itself. Somewhere, right now, someone is working on infinity. A mathematician, late at night, scribbling on a whiteboard, trying to prove something about cardinal numbers or ordinal numbers or some other aspect of the infinite. They're lost in thought, following a chain of logic, seeing where it leads. They're wandering through Cantor's paradise, looking for new paths, new connections, new truths. And somewhere else, someone is learning about infinity for the first time. A student, maybe, reading a textbook, encountering Cantor's diagonal argument, feeling that same vertigo you might have felt earlier, that sense of the ground dropping away, the realization that not all infinities are equal, that the simple can become complex, that the obvious can become strange. And somewhere else, someone is lying in bed, listening to a voice talk about mathematics, feeling themselves drift towards sleep, holding on to the words for a little while longer, then letting them go, then slipping into dreams where numbers might appear or might not, where the infinite might show up as an endless road or an uncountable collection of stars, or just a feeling, a sense of vastness, of depth, of something more. All of this is happening at once. All of this is part of the same thing. The human exploration of the infinite, the attempt to understand what we can barely imagine, the effort to think beyond ourselves, beyond our limits, beyond our finite lives. In a way, this is what makes us human. Not just that we can count, though we can. Not just that we can calculate, though we can. But that we can think about infinity. We can ask questions about the endless. We can wonder about what lies beyond, what comes next, what happens if you keep going forever. Other animals can count, at least a little. They can tell the difference between 2 things and 3 things, between more and less. But they can't think about infinity. They can't contemplate the endless. They can't ask whether some infinities are bigger than others. That's uniquely human, or at least It's part of what makes us the kind of creatures we are. And it's strange when you think about it. We're finite. We live for a limited time, in a limited space, with limited resources. We're small in the grand scheme of things. A speck on a planet, in a solar system, in a galaxy, in a universe that stretches so far we can barely comprehend it. And yet we can think about the infinite. We can hold the endless in our minds, at least partially. We can make it an object of study, a source of wonder, a landscape to explore. This is the gift that mathematics gives us. Not just the ability to solve problems, though that's useful. Not just the ability to build bridges and computers and rockets, though those are impressive, but the ability to transcend ourselves, to think beyond our limitations, to touch something that exceeds all finite boundaries. Cantor felt this deeply. He believed he was in contact with something divine, something absolute. He thought infinity was a way to understand God, to glimpse the eternal, to see beyond the veil of the material world. Whether or not you share his religious convictions, you can appreciate what he was reaching for. He was trying to understand the ultimate, the final, the complete. He was trying to see the whole picture, not just the part we inhabit. And what he found was that the whole picture is bigger than he imagined. There isn't just one infinity. There are infinitely many infinities. Each one opens into another. Each level contains levels within it and points toward levels beyond it. The tower rises forever, and at each level, you can stop and look around and see new structures, new patterns, new truths. But you can never reach the top because there is no top. The infinite is truly infinite, endless in every direction, deeper than any depth, vaster than any vastness. So where do numbers go when they become infinite? They go into this tower. They go into this hierarchy. They organize themselves into levels, each one richer than the last, each one revealing new aspects of mathematical reality. They don't disappear. They don't become meaningless. They become part of something larger, something that includes them but also exceeds them. And it's a beautiful structure, this hierarchy of infinities. At the bottom, you have the finite numbers, 1, 2, 3, all the way up to arbitrarily large but still finite quantities. Then you step into the infinite and you find Aleph Null, the countable infinity. This is where the natural numbers live, and the integers and the rational numbers. All of them have cardinality Aleph Null. All of them can be listed, counted off one by one, even though the list never ends. Then you take a step up and you find the continuum, the uncountable infinity of the real numbers. This is a bigger infinity, fundamentally larger, impossible to list, no matter how clever you are. And this might be Aleph 1, the very next infinity after Aleph Null, or it might be something larger. The continuum hypothesis asks this question, and we've learned that the answer depends on which mathematical universe you're working in, which axioms you accept. But the tower doesn't stop there. Take the power set of the real numbers, the collection of all possible subsets of the real numbers, and you get an even larger infinity. Call it Aleph 2, or don't give it a name. It doesn't matter. What matters is that it's bigger, strictly larger than the continuum, provably more numerous than the uncountable set we just discussed. And you can keep going. Power set after power set, infinity after infinity, each one strictly larger than the last. The tower rises without end. There's no top floor, no final infinity, no largest cardinality. For any infinity you name, there's a larger one, always, forever. This is what Cantor proved, that the hierarchy of infinities continues indefinitely, that there are infinitely many different sizes of infinity, each one distinct, each one unreachable from the ones below it by any finite process. This is humbling and exhilarating at the same time. Humbling because it shows that infinity is even vaster than we imagined, that each time we think we've reached something ultimate, we discover there's more beyond it. Exhilarating because it shows that mathematics can chart this territory, can make distinctions, can prove theorems, can understand structure even in the realm of the endless, and we can follow them, at least for a while. We can climb the tower, level by level, proving theorems, discovering connections, mapping the territory. We can understand Aleph Null, the countable infinity. We can understand the continuum, the uncountable infinity of the real numbers. We can even understand Aleph 1, Aleph 2, and the higher infinities beyond, at least in principle. But we can never see the whole tower at once. We can never grasp all the infinities simultaneously. We're finite creatures, remember? We can think about the infinite, but we can't become infinite. We can't escape our limitations completely. We can only push against them, expand them, stretch them as far as they'll go. And maybe that's okay. Maybe the point isn't to reach the top of the tower because there is no top. Maybe the point is to climb, to explore, to discover. Maybe the journey is the destination. Maybe the questions are the answers. Cantor never proved the continuum hypothesis. He spent years trying, and he never succeeded. But in trying, he discovered so much else. He created set theory. He showed that infinity comes in different sizes. He opened up entire new areas of mathematics. His failure to answer one question led to the answering of 1,000 others. This is how mathematics works. You chase one problem, and it leads you to others. You try to prove one theorem, and you discover 3 more that need proving. You think you're closing gaps, and you find that each gap contains infinitely many more gaps within it. The work never ends. The exploration never completes. There's always more. And now, as we come toward the end of our wandering tonight, maybe you're still here, still listening, or maybe you've already drifted into sleep. Maybe you're somewhere in between, half aware, half dreaming, thoughts flowing like water, images rising and fading without effort. That's perfect. That's exactly where you should be. The mathematics we've explored tonight, these infinite numbers, these uncountable sets, these hierarchies of cardinalities, they'll still be there tomorrow. They're patient. They don't demand your attention. They don't require your understanding. They're just there, quietly existing, waiting for anyone who wants to explore them. You've spent this time letting numbers wash over you, letting infinity brush against your mind, not trying to hold it, just letting it be. And maybe, in some small way, that's enough. Maybe just knowing that this world exists, this mathematical universe of infinite possibilities and endless questions, is a kind of gift, a reminder that reality is deeper than it seems, a whisper that there's more to discover, more to wonder about, more to explore. In your everyday life, you're surrounded by the finite. You count things, measure things, budget your time and money and energy. You live in a world of limits, of boundaries, of things that end. But underneath all of that, supporting it, structuring it, is the infinite. The numbers that never stop, the space that's continuous, the time that flows forever, or at least as far as you can imagine. You're part of that infinity in a way. The atoms in your body are countable, but there are a lot of them, more than you could ever count in your lifetime. The thoughts in your mind arise and fade, one after another, and who knows if there's an end to them. The experiences you'll have, the moments you'll live through, they stretch ahead of you into a future that might not be infinite, but certainly feels long, certainly contains more than you can see right now. So rest in that. Rest in the knowledge that you're finite, but connected to the infinite. Rest in the understanding that you can think about the endless, even though you're mortal. Rest in the comfort that mathematics, for all its abstraction, is ultimately about pattern and structure and beauty. And beauty is something you can appreciate, something you can feel, even when you don't fully understand it. Cantor died in 1918, more than a century ago now. His work is taught in universities all over the world. Students learn about countable and uncountable infinity, about the diagonal argument, about the continuum hypothesis. His ideas are foundational, essential, part of the bedrock of modern mathematics. But more than that, his ideas are beautiful. They're the kind of thing that makes you stop and think, makes you question what you thought you knew, makes you see the world a little differently. They're the kind of thing that enriches your life, not in a practical way, but in a deeper way. They remind you that there's more to existence than the day-to-day, that there are questions worth asking, even if they're hard, that there are mysteries worth contemplating, even if they can't be fully solved. Tonight, you've been part of that tradition. You've thought about infinity, even if just for a little while. You've encountered Cantor's ideas, even if you don't remember all the details. You've climbed a few steps of the infinite tower, and maybe you've glimpsed something there, some pattern or structure or surprising truth that you didn't see before. And if not, that's okay too. Not every exploration yields a discovery. Not every question gets answered. Sometimes it's enough just to wander, to move through the landscape, to be in the presence of something vast and beautiful and mysterious. The numbers will be there tomorrow, and the day after, and the day after that. They'll be there in 100 years, in 1,000 years, in 1,000,000 years. They're eternal in a way that very few things are. They don't change. They don't fade. They don't disappear. They just are, existing in their mathematical reality, patient and constant and true. And you'll wake up tomorrow and you'll go about your day, and maybe you'll remember something from tonight. Or maybe you won't. Maybe you'll think about infinity occasionally, wonder about whether some infinities are bigger than others. Or maybe it'll fade into the background, just another piece of information, filed away somewhere in your mind. Either way is fine. Either way, you've been here, you've listened, you've let mathematics be a companion for a little while, a gentle presence in the darkness, a soft voice talking about numbers and infinity and the strange, beautiful structure of it all. So sleep now, if you're ready. Let your body rest. Let your mind quiet. Let the mathematics continue without you, turning in its own way, generating theorems and proofs and questions without end. It doesn't need you to exist. It exists on its own, independent of observers, independent of minds that think about it. But it's richer when we do think about it. It's more meaningful when we discover it, explore it, appreciate it. Mathematics is a human endeavor, even though its truths are independent of humanity. We make it real by engaging with it, by asking questions, by proving theorems, by wondering what lies beyond what we already know. And tonight, for a little while, you've been part of that. You've wondered about infinity. You've thought about where numbers go. You've held briefly an idea that's bigger than any finite mind, an idea that stretches into the endless, an idea that reveals the structure underneath the surface of things. That's something. That's worth doing. Not because it's useful, necessarily, though it might be. Not because it'll change your life, though it might. But because it's there. Because it's beautiful. Because it's true. The infinite is real. Not in the physical sense, perhaps. You can't touch infinity. You can't see it or weigh it or put it in your pocket. But it's real in the mathematical sense. And maybe that's a kind of reality that's even more fundamental. Maybe the mathematical is the most real thing there is, the substrate on which everything else rests. Or maybe not. Maybe mathematics is just a game we play, a language we invent, a way of organizing our thoughts. Either way, it's a beautiful game. It's an elegant language. It's a powerful way of thinking. And infinity, for all its strangeness, for all its paradoxes and mysteries, is one of the most beautiful parts of it. So as you drift now, as you let go, as you slip into sleep, know that somewhere in the mathematical universe, the numbers are still counting, the infinities are still rising, the questions are still unfolding. Know that Cantor's paradise is still there, still waiting, still offering new paths to explore, new truths to discover, new beauties to appreciate, and know that you can return anytime you want. The door is always open, the numbers are always there. The infinite is always infinite, patient and eternal, ready for anyone who wants to wonder, to ask, to explore. If you're still awake, if you made it all the way through this journey, consider giving this video a like or subscribing to Math for Sleep. It helps others find their way here too. Others who are looking for something gentle to listen to, something that makes the mind slow down, something that brings a kind of peace. Sleep well, dream gently, and if you dream of numbers, let them be infinite. Let them stretch endlessly, beautifully, mysteriously, into forever. Let them show you that the world is deeper than you thought, richer than you imagined, more wonderful than you dared to hope. Good night.